Let's record them. So we form the root array, and we can use the root array in order to find the range of parameters for stability. And this example is about that actually. So this example is as a closed loop control system in which you have a PI controller. We will see what PI controller is. So you have a K plus Ki over S is the controller controlling a system of this type 1 over S plus 1, S plus 2. And there is the feedback coming from here. This is Y of S, the output Y. So we want to find the range of K and Ki for stability. Stability of the closed loop system. T of S, which is Y over R. Okay, that is the transfer function between Y and the R. R is the reference input, Y is the output, as you know. So the closed loop system T of S, which is Y of S over R of S. If you call this K and this one G, if you remember, this was Kg over, well, I should say, okay, let's not confuse you. Let me just call this K of S, and let's call this G of S. This is supposedly G of S. So that this is K of S, G of S. I have done this many times before, 1 plus K of S, G of S, which is, you can write this as Sk plus Ki divided by S. So it is Sk plus Ki divided by S times S plus 1, S plus 2. This is Kg, right? The same thing repeated here. Sk plus Ki, S times S plus 1, S plus 2. Okay. If you equate numerators, denominators, etc., eventually you are going to get the following. Ks, Sk or Ks, Ki plus S cubed plus 3S squared plus 2 plus K times S plus Ki. Okay. So this is our denominator polynomial. Okay, they should all be, all the terms should be positive. So we can say that Ki should be positive, 2 plus K should be positive, which means that K should be greater than 0. That's a necessary condition, but not sufficient. We should do more than that. Actually, we will find that in the using the root array, we can find it S cubed, S squared. So S cubed is 1 and 2 plus K, 2 plus K, and 3 and Ki, right? So S to the 1 is a negative determinant of this, which is 6 plus 3k minus 6 plus 3k minus ki divided by 3 is what we have here. Here you have a 0. For s to the 0, you have again the negative determinant is ki. Negative determinant divided by this is ki. So all the terms should be greater than 0, which means that ki should be greater than 0, definitely, which we could find by the Hurwitz test as well. And also, you should have 6 plus 3k minus ki should be greater than 0, from which k should be greater than, if you do it, ki over 3 minus 2. Okay, so these are the two conditions, this one and this one. K should be greater than 0. So if we have two parameters here, we can maybe plot them in a parametric plane if you wish. If this is, let's say, ki should definitely be greater than 0, so no negative values are allowed. This is 1. If ki is 0, k can be negative 2. So let's say this is minus 2. This is a possibility. And when k is 0, ki is 2 over, no, it's 6, right? So this is 6. When k is 0, ki should be 6. So there is a line that passes, of straight line that passes through here. And this is also, this also limits k equals ki over 3 minus 2 is this line. So this is the region, this is the feasible region. Which means that you can select k and k, this is k, this is ki, okay. K is on this side, k is the y-axis, ki is the x-axis. This region is okay, region, this should be region, okay, that region. For example, if you select it somewhere here, it will be stable, the system will be stable, at least. But if you select it somewhere around here, this will be unstable. Okay. So, do you have any questions about this problem?
Hocam,
Yes.
May I ask something about the previous topic that we use in the transfer function? So we just use the closed transfer function, right? Closed loop transfer function.
Yes.
So the open loop we called is just while we finding GS.
Well, this is the plant transfer function, for example. This is the controller. Closed loop system is plant and controller combined together gives you the closed loop transfer function.
So şeyi hocam hatırlayamadım da open loop nasıldı tam olarak?
Open loop, when there is no feedback, it is an open loop system.
Okay. Okay hocam.
Feedback creates the closed loop. There is a loop here, you see?
Okay.
Backward thing.
Okay, thank you hocam.
Okay, so this is with this example, I'm going to end the stability topic. Well, we will, of course, we are going to use it, but for the time being, I will well, go to something else. And I will look at the general feedback system characteristics, actually. Let's say we have a feedback system in which we have the following. Let's say, again, we have a reference input. Okay. We compare the reference input with the measured output. The measured output and the reference input generates an error signal, E of S, and this drives our controller, C of S. Okay. Now, and this generates the controller output. Now, there are also, I will introduce this here, there are disturbances to the system. I will give you examples about this. Then there is the plant you want to control, G of S. This is Y of S, okay? And this is the output, as you know, system output. And we measure the system output by some sort of a sensor. We can put it here. Usually we are going to take it as 1 most of the time, but you don't have to take it as 1. Maybe I should just, you know, I will take it 1 eventually, but let's keep it here for the time being. So this is the output, this is the measured output. So this is the reference input, error. This is controller output or the actuator. The controller usually drives an actuator like a motor, and there is a disturbance on the system. But what are the disturbances? For example, if you have a car, let's say, you want to keep the speed of the car constant, let's say. Okay. In that case, the car goes along a certain, if it goes along a certain, you know, like road like this, with a certain velocity, the cruise control system can keep the velocity constant by giving the necessary amount of fuel to the motor, to the engine. Okay. Well, it's okay. You give a certain reference speed, let's say 50 or 90 kilometers per hour, and the car goes with 90 kilometers per hour. So this is the output, and this is the reference input is the desired value of output, let's say is 90 kilometers per hour. Then you suddenly encounter a slope on the road. Suddenly there is a slope like alpha or something. So what happens is, well, suppose that this is a car, it doesn't look like it. Now there is an extra load on the car because of this slope. The car has to overcome the slope of the road as well. So that's a disturbance on the car. This is a disturbance, for example. Or if a wind comes, the wind is a disturbance. On an airplane, a wind is a disturbance. On a motor, the external torques might be a disturbances. So you should try to, the control system should try to reject the disturbance as much as possible. Okay. By the way, let me write this. This is the sensor, this is the plant, and this is the control. Okay. Do you have any questions about this up to here? So the disturbances are an important part of the control systems. Well, they are undesired, but they are in the system. You should try to well, the control system not only tries to follow the reference input, but it also tries to reject the disturbance. Okay. So for simplicity, we will analyze this feedback system now and assume that, let's say, h of s, which is the sensor transfer function, is 1, which means that the sensor is perfect, which means that the sensor measures the correct value of your measurement, of your output, okay? Which is a reasonable assumption for many cases. We can, not to complicate things, this is the first assumption we make. Now, we analyze this system now. There are two inputs to this system, two inputs. What are the inputs? One is R of S, the reference input. The second is the W of S. This is the ref input, let's say, and this is the disturbance. Right? Well, we can find the closed loop transfer function that relates Y to R and Y to W. How do we do that? We assume, again, we use superposition. We don't have to use superposition, but we can use superposition in order to obtain our closed loop transfer functions. Well, let's try to let's not do it here. Let's say Y is equal to G times U plus, let's say, W, okay? Which is equal to G times U is equal to C times E plus W, right? And E is equal to R minus Y, G, C, E, which is R minus Y, plus, let's say, GW. You see, you have a GCY here, Y plus GCY is equal to GCR plus GW. So you can put it in the Y parentheses, and eventually you find Y is equal to GC divided by 1 plus GC R plus G over 1 plus GC W. Okay. So this part is the T of S as usual, we say. This is the closed loop transfer function. This is a C closed loop transfer function. And this is called the so-called disturbance transfer function, TW of S. Okay. This is called the disturbance. So what is our aim in this control system? If you look at it here, the aim is to make y equals R despite the disturbance of W, okay? Despite the fact that there is a disturbance, you try to make the output follow the input. For example, in our car example, if your reference speed is 90 kilometers per hour, you want your car to go with 90 kilometers per hour, despite the fact that there is a road slope. Despite the slope of the road, you want the car to go with 90 kilometers per hour. How do you do that? When there is a slope, you press the gas pedal more. Of course, if you are a driver yourself, you would press the gas pedal more. If there's an automatic speed controller, it it opens the throttle a little bit, lets more gas into the engine, which increases the power of the engine, so that the speed of the car remains constant despite the disturbance. Okay, that's how we do things. But we do it automatically. We don't do it, by feeling that the velocity, the speed of the car decreases. The sensor feels that the speed of the car decreases, and therefore it increases the fuel rate to the car, for example.
Hocam, may I ask something before we move on? May I ask in Turkish? Because I couldn't, toparlayamadım da hocam. Disturbance dediğimiz şey, aslında bizim sistemi ilk tanımladığımızdan sonra sistemde gerçekleşen her şey mi? Ekstradan gerçekleşen.
No, disturbance is something something external to the system that you have no control over. For example, the wind, let's say in a car or in an airplane, or the temperature, let's say, outside temperature. Yes, somebody says drag force. Drag force, no, the drag force is possible, but drag force is something you can model and put into your model. Disturbance is external, okay? Something like the wind, as I said, or the external temperature, the things, or an external torque coming to your motor, which you have no control over, okay? Those things are disturbances, and you want to minimize their effect if possible.
So, hocam, also I want to ask, like, in this example, we just say like a cliff, the car just climbs a cliff. So, like, if it goes a long time in the cliff, isn't it become normal to the system? Like now it is just something, yani artık sürekli yokuşta gittiği için
Yeah, well,
o
because of
disturbance.
there will always be a force like this mg sine alpha kind of force that pulls it backwards. Okay.
No, I mean,
Compensate for this mg sine alpha force by putting the engine should compensate for this mg sine alpha if you want to go at a certain constant velocity.
I mean, as long as the alpha is constant and the road is long enough, like if we go to infinity. So like this is something we always calculate and it can't change because the alpha is constant.
Yes.
So like yani disturbance olmaktan çıkmıyor mu hocam artık? Çünkü
Yok.
alfa constant ve sürekli aynı şekilde gidiyor olacak.
On the system, because that force always exists. If that force is removed, then to keep the velocity constant, for example, you decrease the amount of fuel that goes to the engine. That disturbance, if it is there, it is there.
Okay.
It is a constant disturbance. Its effect is eventually eliminated by the control system. That's right, but that disturbance is there.
Okay, thank you hocam.
So make y equals r despite the disturbance, actually, we can make y equals r can be quantified as follows, or we can say minimize the difference between y and r, which is the error, which is r of s minus y of s, as much as possible. Okay. What does this mean? The error, as you remember, is this thing. This is the error. Okay. This is the error signal. We try to minimize this error, and this takes into account the disturbance as well. This height W, let's say. But let's try to find the error. Error is r minus y. Error is r minus y. And y is this actually, as you remember, which is r minus gc over 1 plus gcr minus g over 1 plus gcw, right? This r thing, we have to collect it together. So it is 1 minus gc over 1 plus gc r minus g, the same thing, g over plus gcw. You put it here, so it comes gc plus 1 minus gc. So the final expression for the error E of s is as follows. 1 over 1 plus gc r of s, let's say, minus g over 1 plus gc times w. Okay, so this is the error. This quantity, if possible, we want to minimize this. If possible, you would like to make the error 0, if possible. Okay. Well, in practical systems, you cannot make it, but you might want to minimize this. Let's say that you look at the step response of a system. This is time. You increase R from some value to, let's say, well, this is R something, I don't know, R steady state value of R. Okay. And you would like your system to do something like this, if possible. First of all, you should be having the following conditions. You should have a stable system. That is, your response should not be oscillating terribly or going to infinity. Let's say that this is checked. And also we have time, let's say, domain conditions. Which are like the maximum overshoot, the settling time, rise time, peak time, etc. These should be satisfied as well, more or less, okay? So a good response would give you that. But there is one more thing which I didn't talk until now because I hadn't introduced it. It is possible to satisfy both of these conditions But you might have a response like this now. What is this now? This system would be stable. This is another possible y of t. Okay. This is a good y of t, but this is another possible, let's say y of t, the red one. But the green one has something missing here. And that is what is missing is when the system reaches at a steady state. This is the steady state error. Okay, you want your system to well, if you have a car, you want it to go at 90 kilometers per hour. It makes a jump, and eventually it reaches 80 kilometers per hour, but not to 90 kilometers. Okay, that means that there is a steady state error of 10 kilometers per hour. Or you want your robot arm, the robot arm example, remember, you want it to rotate 90 degrees, but it can only rotate 85 degrees, so there is 5 degrees of steady state error. So the steady state error is steady state error. ESS is the steady state value of y minus the steady state value of the output. Well, what we mean by steady state is things eventually settle down. There is no time dependence, okay? That might be caused by a disturbance. There might be a disturbance on your system, and that disturbance might cause the steady state error. Or there might be, your control system might not be capable of removing that steady state error. But the third thing these are 1, 2 is what we have studied until now. But the third one, the steady state error, is what we will look at now. And this is an important quantity. We should try to eliminate the steady state error, and that will bring us to controller types and so on. That's what we are going to look later on. A very important theorem which we will be using is the final value theorem of the Laplace transforms, which says that the steady state error, which is the limit as t goes to infinity of e of t, okay? When things settle down, assuming that they settle down, is equal to limit as s goes to 0 of s times e of s. We have looked at this in the Laplace transform section, if you remember. But this is a very important theorem which we will be using. But remember that this is true only if the system is stable. You cannot apply the final value theorem if the system is not stable in the first place. You have to assume or let's say guarantee stability in order to be able to use the final value theorem for your system. Okay. What else? Well, I will start analyzing the steady state errors and so on, but we have very little time left, so that wouldn't be enough. The time we have wouldn't be enough, so let me try to do something else. Right. Let me give you an example here. Before analyzing it in detail, let's say that we have a tank system like this one. With a certain height. It has an area A, and there is some flow coming in. And there might be a disturbance flow coming from a rain or something, QD, let's say. This is QI. And this height might be measured and controlled through a valve or something like this. Okay, so this is a valve, let's say. In this system, this is R. This is output flow. Now, the transfer function g of s, which is Laplace transform of qi of s. I'm not going to give you all the details now because we have very little time. Let me just do it this way for the time being. Let's say that we use proportional control. Which means that qi is equal to some k times the error. Error being, let's say, k times h0, the desired value of h minus the actual value. Okay. So the control system we have will be the following. This is h0. This is k. H is somehow measured. Okay. So the closed loop transfer function T of s, we assume no disturbance for simplicity, is kg over 1 plus kg, which eventually comes out to be kr over ars plus 1 plus kr. Okay. Which is, by the way, h of s divided by 0 of s. This is the error transfer function. The error, which is h0 minus h, is equal to okay, this is the error E of s. I have to go it rather quickly because I don't have too much time here. Now let h0 is equal to 1 over s, the unit step input. We suddenly increase the value of the desired value of the height, let's say. Okay. So E of s is going to be this. Now let's use the final value theorem. The steady state error is equal to limit as s goes to, no, t goes to infinity of E of t is equal to limit s goes to 0 of s E of s, which is limit s goes to 0, s times the error, which is this ARS plus 1 divided by times 1 over s. Okay, these s's cancel, fortunately, and these s terms go to cancel because s term goes to 0, and what we are left with is the steady state error is 1 over 1 plus kr. Okay, so the steady state error is not 0. So this control system, if you want to increase the height of the tank, height of the water in the tank, this, even if there is no disturbance, does the following. Let's say you increase it by about 1 unit, but what you can reach is something like this, and this will be your steady state error. This is the steady state error will be your error here. This is versus. So as you increase the controller gain, as k increases, the steady state error goes down, but it is never made exactly 0, as you see here. In order to make it 0 in this example, you have to do something else. And what you should do to do that, we will see in the next lecture. Okay, let's stop here for now.